an artist first learns their craft, they're taught to break their subject down into its basic shapes. Thinking about basic shapes is also a good first step for novice mathematical modelers who are looking to build their modeling skills. Suppose, for example, we were interested in building a model to describe the relationship between the length of a bird's body and its weight. We could build such a model by taking a rather abstract view of bird morphology. Specifically, we could represent a bird's body simply as a cube, the height of which is determined by a given bird's body length, L. If we now assume that the mass density of all birds is a constant k grams per cubic centimeter, then we can arrive at the model we're looking for in relatively short order. Using what we know about the volume of a cube, we would say that a bird's body volume is L cubed, and so its weight W would be equal to the density constant K times L cubed. What we're saying here at the bottom of the screen in words is that weight W is proportional to L cubed, with constant of proportionality K. This victory wasn't really hard fought, and so you might be inclined to question what we've actually done. You might, for instance, ask, is this model correct? I'll suggest that that's not a productive question. All models are in some sense wrong by virtue of the fact that they strip away certain elements of reality. A better question might be, is the model reasonable? Arguably, the answer to this question is yes, the model is reasonable insofar as it's dimensionally homogeneous. A dimensionally homogeneous mathematical model is one whose terms have the same units. It doesn't make sense to add apples and oranges, and so we should be skeptical of mathematical models that do this. That is to say, we should be skeptical of a model whose terms have mismatched units, i.e., models that are not dimensionally homogeneous. A quick check on units shows that we're in the clear on this point. We could measure W in grams. We could measure L in centimeters, so L cubed would be measured in cubic centimeters. We could also see that K in this framework would be a rate expressed in grams per cubic centimeter. Ultimately, both W and the product KL cubed are measured in grams, and so we have apples on both sides of our equation. You could be forgiven for still being a bit skeptical at this point. Maybe you're thinking to yourself that the model is unreasonable simply because you believe it's operationally useless to picture birds as cubes. So let's try to convince the remaining skeptics by tackling this question. Are the predictions made by the model useful? To answer it, we'll turn to data. To put our model's predictions to the test, I compiled a list of 24 species of birds common to eastern North America, 8 of which are shown here. For each species, I found the average weight and length, then plotted the results in LW space as shown here. Each black circle on this plot corresponds to an observed pair of length-weight measurements for a given species. Overlaid on these data points is a plot of the curve KL cubed, with K set equal to 0.006. The match between the curve and data points looks good, but it doesn't at this point look substantially better than, say, the match given by something like a constant times L squared, indicated here by a dotted curve. It's actually a bit difficult to assess the match between curves and data visually in this example. The problem stems from the fact that data points near the origin are too clumped, while those further from the origin are too diffuse. To help ourselves out, we can turn to a transformation of the data involving logarithms. You might wonder, why logarithms? It's because logs tend to break up tight clumps of data points and gather together groups that are too spread out. Here's an illustration showing you what I mean. Consider the plot of ln of x. It's got a vertical asymptote. It increases rather quickly, cutting through the horizontal axis at the point x is equal to 1, and it tends to increase beyond x equals 1, but in an ever decelerating manner. Now consider 2 points clustered close to one another near the origin. Maybe the 2 points are weight measurements, or maybe they're 2 length measurements. It doesn't much matter. The point is that one of them maps to this spot in the range, while the other maps here. In the end, they end up farther apart. Next, consider measurements farther from 0 and farther from each other as well. In this case, we can follow the path from the domain to the range to find that transform measurements have been brought closer together. Turning our attention back to the match between our model and the data, we see that the logarithm strategy does indeed help. Here's a plot of log weight versus log length cubed. Logs have clearly resolved our earlier problems with clumping and dispersion. What's more, the scatter now suggests that the relationship between log transform variables is well captured by a straight line of slope 1. This linear relationship, or rather affine linear relationship, is to be expected. Applying what we know about logarithms from high school to our mathematical model, we see a familiar formula for a straight line emerge. Here, ln k is the intercept. With a little bit of algebra, it's possible to show that ln k is about -5.1. This corresponds to a k value of about 0.0061. That's close to the value we used in our earlier plot, which is heartening. Another heartening aspect of the plot is that the straight line that corresponds to the competing model based on L squared isn't actually a good fit. In this new light, a model based on L squared rather than L cubed would predict that the data follow this line of slope 2/3. So it seems we have a pretty good story now. We've adopted a perspective based on simple shapes and argued that a bird's body weight can be modeled as its body length cubed multiplied by a constant of proportionality. We've got support for our model in the form of a good match to data, and we've even used the data to come up with an estimate of the value taken by the constant of proportionality itself. There is, however, one remaining problem. I suppose it's arguably a problem, but in any event, it's worth discussing. In the top right corner of the plot, we see one lonely data point that seems out of step with our model. What's going on with this apparent misfit? If we go back to the data and dig a little bit, we find that the outlier is this guy, the great blue heron. What's noteworthy about great blue herons is their shape. They look a bit more elongated than other birds in our data set. The implication here is that a key assumption of our model has likely been violated. As we've said, our model treats birds as cubes, specifically scaled up or scaled down versions of the same cube. So, as far as our model is concerned, a small bird has the same proportions as a medium-sized bird and the same proportions as a large bird. By including the rather gangly heron in our data set, what we've possibly done is confront our model with a situation like this. That is to say, we've challenged our model with species of birds whose proportions change as they increase in size. Disproportionate growth of the kind we seem to have uncovered is common enough in nature that biologists have introduced some terms to describe it. When discussing proportionate growth, for instance, the term isometry pops up. Two traits are said to be isometric if their relative sizes remain constant during growth. Here, growth could be observed during development, or growth could refer to the size changes we observe as we compare different individuals or different species. If traits x and y are isometric, then we could say mathematically that y is proportional to x. Applying a log transformation would lead us again to a relationship that could be described by a straight line of slope 1. As an example, notice that the model we built, w is equal to kl cubed, posits an isometric relationship between weight w and volume L cubed. When discussing disproportionate growth, the term allometry is used. Two traits are allometric when they change at different rates during growth. Ultimately, allometry drives the changes in shape that accompany changes in size. In mathematical terms, x and y are allometric when y is proportional to some power of x, some power n other than 1. In log-log space, an allometric relationship could be described by a straight line, but the slope of the line is n, not 1. Going back to our model, we could also get away with saying that it posits an allometric relationship between weight w and length L. Allometry is a very important phenomenon in biology. To appreciate its importance, consider a typical bone. It turns out that the maximum compressive force a bone can withstand is proportional to its cross-sectional area, which, by virtue of the fact that it's an area, scales like body length squared. As we've seen though, weight is predicted to scale as body length cubed. So, if we increase the length of an individual without allometry, in other words, without changing its shape, then the individual's weight would increase more quickly than its skeleton's ability to support it. With this in mind, it makes sense that outliers like the great blue heron cropped up at the size extremes of our data set. It also means that we might wish to limit the application of the model we developed here to birds of similar size. By doing so, we'd hope to minimize the chance that allometry upset our cube-based view of birds. We've covered a lot of ground, so let's wrap up with a recap. We built a model for the relationship between W and L based on abstract geometric reasoning. We then tested the predictions of the model using data. An outlier led us to suggest that a key assumption of the model was violated. Since similar problems occur elsewhere in biology, especially as we increase the range of sizes encompassed by our model, we ultimately thought it wise to limit the application of our discovery to birds that are relatively close in size. By the time you've mastered the ideas I shared in this video, you should be able to do at least 3 things. First, you should be able to build a simple model for the relationship between 2 biological features based on direct geometric reasoning. Second, you should be able to articulate the key assumptions on which your model depends. Third, you should be able to explain how you would use data to support the claim that 2 biological features change in an isometric or allometric fashion. If this seems beyond your grasp at the moment, don't give up. Make sure you complete the assigned reading and try the exercises. Before you know it, you'll be modeling like a pro.